Hello, hello. Can you hear me? Anyone? I hope I'm audible. So, in the previous class, so this is our ninth week, and in the previous class, we have talked about, or we have rather discussed the initial part of the coding of the Hatipox, so which we are gonna finish today. So before doing that, let's do one of the. So I have taken two problem from the Zabo. This is one of the problem where you are asked to prove the average of any operator, which is actually basically if you take the trace of the your density and that operator. So which is a very simple proof but useful one. And this is another one where actually you have learned uh, this matrix element, which is your IJAB, that is actually given from the Slater's rule, but actually we can prove that given the Hamiltonian in the second quantization operator. So we are gonna solve these two problem in this class. So let's first solve this problem, then we'll finish up the Hartree-Fock coding, and then if we are left with any time, then we'll come back to the second problem. Sounds good? Okay, so let's read out the question first. It says that uh, consider a quantum system described by a mixed state. The described by a mixed state. The system is known to be is in one of the several pure states. So actually, your state psi is made up of different pure state psi I, and with a corresponding classical probability pi. And you are giving any observable a, and you have to calculate the ensemble average, or which is basically the expectation value we know in terms of our quantum mechanics. So can we prove that the average value of any operator is basically when you take the operator form of your density and the operator from your a, and if you multiply it, you do a matrix multiplication, and if you take a trace of this matrix multiplication, then that is basically your average value. So take some time, maybe 2 3 minutes, and if you try to solve it, then I'll show you the solution.
Pure states here means stationary states, right?
I cannot hear you. Sorry,
Pure states here means stationary states, right?
your voice is very feeble. I'm sorry, but I can't hear anything. Your states here. Stationary state. Um, I do not mean in that way. I actually pure states means is that um, you know exactly in which state your system is, right? So that is actually pure state. But if you don't know in which state your system, then it's a mixed state. So for example, if you know that you have made a system, hydrogen system, and one electron in the 1s system. So exactly you know your electron is the 1s system, and you can write the wave function. So that is your pure state. But if you don't know exactly the how you represent the state of the system, then but you know that it is made up of some of the states. So then that is called a mixed state. But yeah, in this case, Um, so okay, so let me show you the proof, then maybe it might be clear. So we need to prove that the average value of any operator A is basically the trace of rho. That we need to prove, and we are given that the rho is a density operator, and you all know that when you write an operator, it is in the outer product, it's not the inner product. Okay, so you are given that your rho or the density is so for a pure state. So if your state in the psi I, then you know your density looks like this. This is for your pure state. Right. Now, if you don't know that your state is in the psi I state, but it is made up of several psi I, then your the your density is basically the weighted sum of this psi I. Right. This is very trivial. Now, now let's write this A. So, um, so if your state is a very pure state, then AI is basically psi I A psi I. This is the simple expectation value approach. But if you don't know your state is in the psi I, then your A is basically you write as a summation of Pi psi I A psi I. Right. So this is your expectation value in the mixed approach. Now let's say in this place, so you have a we have done this several times, that if you have a state vector which is a complete set, so you can write from the resolution of identity that summation over n, this is your, so we are going to put it in here, so it becomes Pi psi I A n n n, this is your 1, and you are left with psi I. Now you have two sums over n and I. Now you have psi I, then A, this n, and you have another number psi I. Now you can see this is your two inner product. This is two inner product, and that will give you two numbers. So actually you can switch their places, right? It is legal to do it. So you have Pi n psi I, and here you have psi I A n. Okay. Now another simplification you can do is that, so this Pi is a number, this is a number, this is a number. So you can take this summation. So rather you can write summation over n. You have so n. So you can take the summation inside here, and now you have pi psi I. I think it is better to write in the next page.
I didn't understand the last step actually.
Huh?
Can you hear me? Can you hear? The last
Sorry?
step, can you? The last step.
Yes, so in the last step, what I'm going to do is that, so here you have two summation. One is over summation over I and one is over n. So you are talking about this step
Yeah.
or the next step that I'm going to do right now?
No, this.
This one?
Yeah.
Okay,
Yeah.
so what I did here is that, so in this place, I put a resolution of identity. So which you can see from here. So, and in that step, so this is becomes your psi I, A, and N. So this is the item that I have written it here. And you had another item that is your this one that I have written here, and your PI is a number. So this is your this line. Now in that line is that this is the inner product. So this will give you a complex number, and this is will give you a complex number, right? So if like as is a number, so you can switch them or you can actually permute them. So that's what we did here. We have taken this inner product in the left hand side and the other left hand side to the right hand side. So now what we are going to do is that, so let me again write that down. Summation over n pi n, and here you have psi I a n. Right. Now we can write it n I, or so this pi is a number. I can put it inside here because this is just a number, right? So it is becoming pi psi I a n. Right. Now you can take this summation also inside because your n, this variable doesn't depend on this summation. So actually what you are doing here is that n sum over I pi psi I psi I, or you can remove this one psi I, then you have a and n. So this quantity is basically what is given to you, your rho. This is the density operator in the mixed state. So you just place summation over n rho a n, and this is nothing but, so you are taking a sum over n, and this is your matrix multiplication between the operator of rho and a, right? And you are taking this element rho a n an element, and if you do the sum, this is basically nothing but doing rho a 1 1 rho a 2 2 plus dot 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 up to nn. So this is just a trace, or if your matrix, and you are taking the sum of the diagonal limits. So this is the, and this is a very useful theorem, is that if you have the information about the density of your state, and you know the matrix form of the operator, then you if you take the trace of row A or A row, so basically trace of AB is equal to trace of BA, so it doesn't matter the way you multiply, but if you take the trace of row A or A row, you will get the average value of the your operator. So sorry. So that was the proof. And in the second part, um, this is the this will take some time. This is the, I think, Slater rule number third. So that we are going to prove using the anti-commutation relation of the annihilation and creation operator, and the normal ordering of the operator string that we are going to do. But it will take some time. So I think it is a good idea to finish off the Hatrifa coding first. Then we'll come back to this problem. Uh, so any doubt? Do you have any doubt so far uh, in this coding part? Okay, so yes, so we have done up to, I think, step 5, I would say. So we have read the file, and we have calculated the nuclear repulsion energy. Then we are given the kinetic energy integrals, the overlap integrals, the kinetic energy integrals, and the nuclear attraction integrals. And we have read that file, and we have taken all the like all the permutationally unique integrals, and then we fill in the blanks, like whatever the place needed to be, and then we calculate the whole kinetic energy integrals and the potential energy integrals. Then we take the sum and we form the core, like H core in this line, right? Then we read the two electron integrals. We have taken this eightfold permutation symmetry. Then 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 using, like, this will be used in here. I think yes. The new, when we'll form the new Fock matrix, it will be used here. I think I haven't done here, but yeah, we'll do it. And then we have did this. We have diagonalized the overlap matrix. Then taken that diagonal matrix. We have computed the root over of minus half. Then sorry, to the power minus half, and using that we form the s to the power minus half. Then using that s to the power minus half, we have, so this is our initial guess, H core, right? So you take only the H core, that is the initial guess. You haven't taken the two electronic contribution. So using that fork, we have diagonalized it, and we got the matrix. Then we have transformed the matrix to the original basis, right? To the original non-orthogonal basis. Then we form the density d0 mu nu. I think up to this part we have done it here. Yes. Then our next step is to compute the initial Hartree-Fock energy. So let's run the code once. It is allocating a runtime here. So have you practiced the rest of the part, Diptonu?
No, I could not get time actually.
Sorry.
This week I could not get time actually.
Oh, okay.
Practice.
It's fine.
I have to look at the code again.
We got some
So
error.
we can at least look at the steps given in the repository, right?
Uh, your voice is too feeble. I don't know why today. Actually, I can't hear you. Okay. Oh, okay, okay. I got the error. It's my bad. So it's saying that is that they are unable to open the file because what happened in the collab is that if you if you are disconnected, so they are given a runtime here. Okay. So now when you so in the initially we have uploaded all the files here, and when the runtime is over, they actually delete it from here. So you have to again re-upload it. So we'll do it. Just give me a minute. So these are the files. Uh, we will update. So ensure that your files are saved elsewhere. The runtimes files. So these runtime files will be deleted when this runtime is terminated. So that's why. Yeah, I think now there will be no error. Yes. So we have total number of 7 OAOs and these. Okay. Let's go to the next part. Compute the initial Hartree-Fock energy. So for the Hartree-Fock energy, what do we need? So you can see one thing. Whenever you calculate any energy or any average value, actually that will give you a number. So that won't be any matrix. So all the contraction is happening. So in here, if you look at very carefully, it's what happening is whatever I have given you in the question. So in the question I have given you, if you take the trace of the density matrix and the operator you are interested in, you get the corresponding average value. So if you see, this is your density matrix and this is the operator whose like expectation value you want to calculate, and this mu nu, when you are doing this mu nu, so this is basically nothing but the trace of the matrix matrix multiplication of your density and the operator. So that's the way you are getting your electronic energy, and that's what we are going to calculate it now. So um, let me see, how did I write? Yes. So E electronic. So remember, this is your electronic energy. If you add the nuclear repulsion term, what we have defined here. Uh, yes. So if you add the nuclear repulsion term, then you have the total energy. But whatever we are calculating here in the Hartree-Fock, that is your electronic energy. So E electronic energy. What is the expression they have given? The expression is that d mu nu and h core mu nu plus Fock mu nu, right? So again, here we'll use the np.einsum. So numpy.einsum. Now you have to give two strings. So you can see here mu nu is actually getting multiplied with another mu nu and is giving you nothing. So here actually what will happen? So let's look at this term. Here when you form the density, it is mk and nk. So you have, so if I don't see whatever is written it here, I can see it from here that my whatever the argument I am passing, that is a two-dimensional matrix which I am representing as mk, and the second matrix that is also a two-dimensional matrix which I am representing as nk, and now the matrix multiplication is over the second index of the first argument k and the uh, second index of the second argument, and the resultant matrix, what I'm representing here as a density 0, that is also a two-dimensional matrix and which is represented as Mn. But here, so you are given a mu nu, so let's write Mn, and again here it's a sum, so H mu nu plus F mu nu. So this is a, so it's a two-dimensional matrix, and you have another two-dimensional matrix, you are summing it up, you have another two-dimensional matrix and whose dimension is also Mn, and it is giving you nothing, so you keep it blank here. So this is the way you do it, so it will give you an like only a number that I'll show you. So what is the first argument? The first argument is the d0, right? The first argument, and second argument is the h core plus fog. So h core plus fog f0 dash. Yes. So this is your fog matrix, right? So this is your total whole, like the second argument, and this is your first argument. So up to this is fine, but just for letting you know is that there are options that we actually use it very regularly. So when you are dealing with a large tensor where it's a four-dimensional matrix and the calculation, so this step is the actually the costliest steps in any electronic structure calculations. Like if you do an einsum with a large matrix, so what we do here is that there is a option called optimize is equal to, that is you can pass it true, or you can write optimize is equal to greedy. This is just a coding thing, that if you use this optimize is equal to greedy, this step will be calculated faster than the normal one. So it is, I don't know how they do it, but as far as I know that so when you have a large matrix, the contraction scheme, if you give greedy or true, they find an optimal path where the contraction happens, and it becomes very fast. I don't know the exact detail of this, but this is just a thing. So let's run it. Yes. So let's print the initial electronic energy. It is coming around 1 minus 129.844, and I think they have given the initial electronic energy which doesn't match. Yes, it is given minus 125.844, and we are getting 129.8453. So this is the problem that I have also faced during my initial coding, that it doesn't match with their initial energy given. But yes, this is none of our business, because this is the guess energy. We haven't done any kind of iteration here. We haven't done any kind of self-consistent iteration. So we need to match the final energy whatever is given here. So the final energy, so the energies for the each iteration is given here. So the final energy has to be matched. But the initial energy, I don't know. I have checked it several times, but it doesn't match with their energies. I don't know why. But yeah, the final energy has matched. So this is the initial energy that we have calculated. Now, yes, now compute the new fog matrix, right? So this is step 7. So initially the fog matrix, the guess we have taken was the H core. Now we have to build the fog matrix, and for that, so now you can see it here that it is a four-dimensional matrix. So what we have calculated here in terms of ARIES, electron repulsion integrals. So This is the integral, and this is a two-dimensional matrix. So now if you do it here so you can always write a code like in using a for loop. So I can, if you want, I can show you. Do you want to see that? Can you write a uh, for loop code to compute the electronic energy, or is it the numpy.insum is fine up to you? Okay, so if I have time in spare time, I'll show you that. So the for loop will be very slow. So what you will actually do is that uh, so here the sum is over mu and nu. So your for loop will start. There will be two loop. One is over mu. So what you will do is that for mu in the first dimension, then again the nested loop for nu in which goes from 0 to range blah blah blah, and then you calculate the mu newth element, and again you take this and you take the matrix multiplication and you sum it, and whatever the last sum, that is will be your electronic energy. Okay, so if you are interested, I can show you, but this is the much faster way in the einsum, the einsum I have shown you here. Well, so in the okay, so in the step 7, let's define a mat define a make fork. And for the fork matrix, what do I need? I need the H core. You can see it from here. You need the H core, you need the density, and you need the two electron integers. So these are the arguments that we are going to pass: H core, Aries, and density. Right. So you write fork is equal to 2 times numpy dot insum. So we are calculating this element first, then we'll later add this H core. So what is the first element? The first element is the 2 times your electronic repulsion integral, which is mu nu lambda sigma times the d lambda sigma, right? So I have written 2 times numpy dot insum and ls mn ls. So ls means L for lambda and S for sigma. So ls, and you have mu nu, so mn lambda sigma ls. So ls mn ls, and what it is giving you in return, it is giving you a mu nu, so mn, right? And what is the first argument? That is your density, and the second argument is the Aries. Right? Now fork. So now we have to calculate the second term. This is your second term, and in the second term you have to calculate this second term also. So it's a plus minus minus, so it will be a fork minus equal to. So when you do a minus equal to, so that is basically, so you can write a is equal to a minus 5. This is uh, the way you write, but you can also write it in that way: a is equal to minus equal to 5. So that actually means that a is equal to a minus 5. So here fork minus equal to this means fork is equal to fork minus whatever I am going to write it here. So this is basically again the lambda sigma. So let's copy it from here. Yes. So the first index is LS. So lambda sigma LS is fine. And the second is MNLS. But you can see it here. It is actually mu lambda nu sigma. Right. So this is so sorry. This is MLNS. So MLNS. Any doubt so far? Okay. So this is your fork. Now the first term plus equal to. So we have to just add the H core. So now it will be H core. And we want to return the new fork. Return the fork. So this is our step 7. So let's copy it and paste it here. So we have defined the fork wheel. So whenever we need, because it's an iterative process, right? We have to calculate again and again and again. So that's why I have defined a function for it, right? So yes. Now the hardest part, that is the self-consistent field. So before that, let me tell you one thing is that, so you can see when you calculate the fork matrix here, what is written here, I minus 1. So the I minus 1 actually dictates the density for the last iteration. So initially we are in a, so initially the H core is our fork. We have taken the H core as the initial guess, and from there we make the density. So whatever the D0 we formed here, D0, this is our initial density, right? Now using this D0, we have made the fork. So again, we'll diagonalize it, and whatever the stuff we have did here, we'll do it again here. So now you will get a new coefficient matrix, the new density will be formed, right? So we have to keep track of the previous density as well as the new density coming out from the diagonalization of the your fork matrix. So this is one thing, and another thing is that when you check the convergence, so where is it? Yes. So when you check the convergence, so you need the electronic energy from the previous iteration. So in our case, so as we are in the just 0th iteration, we haven't started the iteration yet. So whatever the initial electronic energy we have calculated here, initial electronic energy calculated, this is our previous electronic energy. Now when we will form the fork and diagonalize and again the new SF energy, that is our new electronic energy. So this is the two information that we have to save it here. So let's do it. Mm, so right, density old, this is basically your D0. This is the initial density, and electronic energy old. Electronic energy old is basically the E electronic 0. These two things we have calculated. Yes, right. Now let's define the variable, some of the variable. So what is the maxed iter? This means that how many number of iterations I want to perform. So when I do a self-consistent field, what I do actually is that I open a for loop, and within that loop, I keep calculating the electronic energy unless or until it's converged. So there might be some problem. Let's say you have, it is 500 iteration, 600 iteration. You cannot run it for lifetime, right? So you have to define a max iteration. So we are defining, okay, we'll see up to 100 iteration. If it is work, like if it works, it works. If it doesn't, so there is some problem. We have to pass a better guess. We have to fix something if there is any problem that the Hartree fog is not converging. Yes, there are several problems and many advanced solution to that. There is very famous thing, I think, that is also there in the programming here. They have, that is your DIIS, direct inversion of the iterative subspace. Let me show that, like, let me CCLT. Not this one. Yes. DIIS exploration for the ACF procedure. So if you are interested, you can see this is actually, you calculate the error matrix and other stuff. So this is a bit advanced. So you can see is that the code we are writing, it took 39 iteration to converge. Now with the DIA extrapolation, it took only 10 iteration to get the same energy as this. So this is very faster. So so this is, you can do it. It's not that hard. If you actually can code the Hartree fog, you can code the DIS of that. So yes, this is project 8. You can try it yourself. Okay. So what we are doing? Yes, let's define the max iteration as 1, and we have to define the energy threshold. So how many digit I want to uh, like get the iteration done. So let's say 10 to the power minus 10, and we need the residual threshold. Let's define it also as 1 at 10 to the power minus 10. So what is the residual? So you can see it here. We need 2 threshold to check the convergence. Yes, or RMSD. This one, this is I'm defining as the residual threshold, and this is your energy conversion. So this delta 1 I have defined as 10 to the power minus 10, and this delta 2 I have defined as 10 to the power minus 10. Okay. Now um, let's define a function. Yes, I have it here, and this is the main function that defines that SCF iteration. SCF iteration. Or what are the parameters I need it here, or what are the arguments? So you can see I need the S half fork, right? I need S half fork and the previous electronic energy, the previous density, right? And the max iteration and whatever the threshold I have defined. So I need all of those information. So I'll pass it here. So I need S half. I need E electronic old energy to check the convergence. I need the old density to calculate the residual. I need the H core to calculate the Fock matrix. Yes, I need the Aries also. So you can see that, sir, why do you need the H core and Aries? That is already been calculated in the Fock matrix. So actually inside, so Fock matrix is formed multiple times, right? So initial this function, I'll call the function that I have defined here. So I need to pass this, whatever it's needed here, I have to pass it here also. So that's why I need the H core, Aries, and density old. Yes. So I'll get the Fock from here, and now I need the maximum iteration, energy threshold, and residual threshold. Yes. Okay. So we need a good printing style. I have already here. So I'll copy it from here. This is just a formatting. You don't have to worry about it. So it will print the iteration, and it will print the electronic energy and what is the convergence and the residual convergence. It will print it, and it will print a hyphen line up to 60 times. It's just a way of it will look good. It doesn't anything. Okay, now start the iteration. So to start the iteration, we'll open a for loop for I in range maxiter. Do you guys know what is range, or I should explain? I think you know the meaning of this line.
Yes. Like,
Okay. Okay. So what it will actually do is that it will start from I is equal to 0. So let's say your max iter is 10. So it will go from I is equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it will stop max at max iter minus 1. So Python is not inclusive of the last index. So but in Fortran, if you start from like 1 to 10, it will actually go from 1 to 10 up to 10. But in Python, it will stop. Actually, it's a geo-based indexing, so it will stop at whatever the number you are giving. So here we have given 100, so at 99 it will stop. Okay, let's let's print the initial energy. So what is the initial energy? If I is equal to 0, this is your initial so this is your initial iterations, like. So I want to print formatted string. So I'll just copy it. Even I really don't remember how this formatting works. It's just the way of printing. Yes, so this is for the electronic energy. Now let's make the fork. So this is the iteration, right? We have calculated up to initial energy. Now whatever the step 7, it will be iteration. So step 7, step 8, step 9, and step 10, these all are part. So you can see return to step 7 and continue from there. So from step 7 to step 10 is basically that should be in the iteration step. So your fork, let's make the fork, make fork, and for fork we need to pass the H core, Aries, and density. So you need to pass H core, Aries, and density, old, right? So this is your fork, and now the other parts will be as simple. So we think we have done it. So I think they have given the fork matrix to check. Yes, the new fork matrix they have given. So uh, uh, let's check it out once whether we're getting the same matrix or not. Yes. So this is the new fork 7 by 7. So let's print it. Print fork and exit. So otherwise it will go iteration, right? So just I'm putting a exit here. Oh, okay, sorry. So we haven't called the function yet, right? So let's put it in the here. and then call the escape iteration function. Sorry. Yes. So here I have to pass the D0. I think other things should be fine. Yes. Uh-oh. I put an exit for I in. So 1.88. So it is actually 18 point this. Yes. And this is 18.813. And the last number is 0.14503. And the last number is 1.4503. But let me check why the other iterations are going. Print fork, and I put an exit here. Why it's not exit? No, they're printing all the. It should not be the case. Okay, whatever. I have to check it that why it's not exiting, but maybe it's not coming to this. Uh, let's see. The fourth. I don't know why it's not exiting. Yeah, okay, whatever. So we have calculated the first fork matrix. The second is uh, we have to calculate the we have to orthogonalize it using the S half. We have already did it. So you can see we have already did it here. Uh, so this is the step. So we have to do it again here. So yes, we have made the fork, and now let's get the fork dash in the another basis, which is basically S to the power minus half dagger fork S to the power minus half. So you are given S half dot T. You can take dot conj, so that will actually give you the that will actually give you the if you are dealing with the real matrix. So here we are dealing with the real matrix, so dot conj doesn't matter. We'll take only dot T, and now you take the matrix multiplication. S hub dot T fork, and then you have S hub. So you got the fork in the dash. Then again you take the epsilon and the C dash. If you diagonalize it, right? So this step, if you diagonalize it, you will get the orbital energy and the coefficient matrix. So you have to do np dot lin algebra dot eig. So you can use EIGH because your fork is Hermitian. But yeah, I'll use the EIG. Now you got the epsilon and C dash. Now let's transform the now this step back transform. Right. Mm, so you have to multiply with s to the power minus f and C dash. So your C becomes S half. Whatever the step given here, I'm just following it. C dash. So this step s to the power minus f and C dash. And now let's form the density. Right. This density, we have already done it here. Here, D0. So we have to calculate the density. Right. But yeah, I told you one thing is that if when you use the EIG, then it doesn't mean that all the lowest energy will come first and the higher energy will come at the last. But it is better to sort it so that all the lowest energy will come first, then the other one. So what you need to do is that you have to so what you have to do is that you take the argument np dot arg sort and pass the epsilon what you have got from here and use this epsilon is equal to epsilon, and if you pass the argument it will sort the value from the I'm not explaining all these steps because I have already done explained these steps here. So yes, I've explained previously that why do you, like when you use the EIG, then actually when you do the np.arg sort, you get the arguments and then it will sort it, and the same way you have to do for the coefficient because it will shuffle the place and you have to do it for the coefficient. So that I have already discussed. That's why I'm not giving much time here. So yes, if this part is done, then again you equalize these two. C, you take all the rows and here you pass the argument. Yes, now it is sorted. Sorted. Now using this form the density. Right. This is your density. This is your new density because you form the fork, right? You form the fork dash, then you have diagonalized. So now this C dash is your new coefficient, and using this coefficient you actually form the new density. So here it will be C0, C0, right? Yes, but I haven't. Uh, Okay, but I haven't passed any NO. Give me a moment. Okay, so your new density is formed. Now you have to calculate the escape energy. N E electronic. So we have already the old electronic energy. So we have to calculate the new electronic energy. New is equal to the same formula. Yes, this one, right? NP. So we have already explained. So new escape energy, you have to pass the new density. So here you have to pass the new density or density new, and the H core will be same, but the fork has changed, right? So H core will remain same, but your this will be your fork or fork dash, right? Yes. So this is your, so this fork is in this fork is in the dash basis set, but here you have to use the fork only. So this is your F new mu, and this is your new electronic energy. Okay, now you got all the things. Now you check the convergence. Check the convergence. Check the convergence. Okay, so delta, calculate the RMSD. I'll show you how do you calculate. So look at this expression. So in this expression, what you are doing here, you first take the difference of the density in the ith iteration and that was in the previous iteration. You take the difference. Then you square it out. You have taken the square. Then you are taking the mu nu. So you are taking the trace or you are summing over all the indices. Like you are summing over all the mu nu. Then whatever the number you have got, you take the root over of half. We'll go step by step. So the first step is that you calculate the new density minus the old density. Okay. So you take the new density minus the density old. The first step. The second step is that whatever the number you got it here, you square it, right? You have to take the square. And this is a matrix, so you use np dot sq a np dot square and you pass the matrix. Yes, it is done. Now, so this step is done. Now you have to take all the summation of all the elements. So now you have to do RMSD is equal to np dot sum RMSD. So whatever we have calculated here, we have passed it here and we got the summation. And simple. Now your RMSD, the last step is the square root of that number. This is just a number, right? So now np dot sqrt RMSD. So you have calculated the RMSD. This is your one convergence check, and the second convergence check is the difference energy. This is very simple. This is basically E electronic new minus E electronic old. Right. Okay. One thing is that now this difference in energy, so if your new energy was higher than the electronic energy, you will get a positive difference. If it is lower, then it will get a negative difference. So it may oscillate between the positive and negative. So what you can take instead of this, that you can take a absolute energy of this difference. So absolute means you will not care about the sign of the difference. You will only calculate the number. Okay, if it is converging up to fifth decimal, sixth decimal. So our criteria was up to 10 decimal, right? So if it is matching up to 10 decimal, I do not care about the sign. So we are taking the absolute difference. So this is your difference energy. Now check for the convergence. If, right, now let's print it first. So I'll just copy it from here. Yes. So I have printed the new electronic energy, what is the difference I got, and what is the residual norm of the matrix. Now you check the convergence. If difference energy, so when I should stop the convergence, if the delta energy or the difference in energy is less than the energy threshold I have given, as well as, so I have to put a and here, I cannot put or. So this means if my difference is energy is lower than the threshold I have given, and also the residual is also lower than the residual threshold. So if one of the condition field and another one doesn't like fill, it will not stop. It will go to the next iteration. It has to fill the two iteration, like two conditions simultaneously. That's why I am putting an and here. So if RMSD is less than equal to the residual threshold, then you can break, then you can break the convergence, and you can print SCF is converged. Okay, let's say if it doesn't converge, then what is the step? The step is that you have formed the density nu, right? So in the second step, it will go back to this statement. Now it is not zero, right? Now it will go back to this fork. Here the density old is being used, but this density will be taken from your the dense d0 that you have calculated from here, right? Where was it? Yes, it was here. So it will be calculated from here, but it is an iteration. You have to update the value. So the new density you have calculated here, the new density, yes, this new density in the next step. So in the coming iteration, that should be your old density. So you have to just add a line here that your density old is now the density new. So you have updated the old density, and again the electronic energy. So that's what I have discussed in the previous, that you have to update these two energy. So E electronic old is basically the E electronic new, right? Now you're done. You, and if it is converged, so now return. So this is a function. You are inside a function. So we have to return something, and in return you have to give the E electronic new and the new density. Okay. Now call it here. So I think I have calculated. Yes. So electronic energy, and new density is equal to the SCF iteration and this. Let's run it once and see. So it is printing, SCF is converged, and this is your iteration value. So check. So this is your first iteration, and you got -129, whatever the value you got. This is your initial iteration. So that's why 0, and this is your first iteration. So in the first iteration, so the value is actually dropped. So what is the delta E? This is basically, you can see, around 51 atomic unit, which is huge. -129 to -78. So this is huge, right? And this is your RMSD, which is also high. So your iteration didn't converge. Then it goes to the second iteration. Here also the energy is pretty high. So now let's check for, let's say, 23rd iteration. Here the energy difference is 10 to the minus 9. So if you have given 10 to the minus 9 or minus, so when you got the iteration here, for example 28, your energy value is 10 to the power minus 11. So that is actually below 10 to the power minus 10. So then this iteration should have been converged, right? But no, you check the RMSD, it is also greater than the 10 to the power minus 10. That's why it didn't convert. Now when your iteration, the RMSD is 10 to the less than 10 to the minus 10, and energy is also minus 10 to the power 10, it got converged. And this is your electronic energy, right? This is your electronic energy. Now you are actually done. You got the electronic energy. You add the nuclear repulsion. So let's print the total SCF energy. What is the total SCF energy? This is the sum of the electronic energy and the nuclear repulsion energy plus the E nuclear repulsion energy. And that is in which unit? That is in atomic unit. And after this, so this is your total SCF energy of the H2O molecule in STO3G basis. Now let's check something. So this is the STO3G basis. So we have taken in the STO3 basis. This is the file that we have uploaded here, and see that the SCF energy is -82.9444 whatever, right? And it took around 31 energy. This is one thing to note, that it is -82.944. Second thing, please note that the total number of atomic orbitals is 7 here, right? And virtual is 2. Now let's go to a higher basis set. So okay, so first let me show you that our energy is matched. So it is -82.8444699,003, right? And we got 6900. And if you actually increase the iteration, like 12, let's say 12 and 12, I think we can match the number. Yes, so around 37 iteration. It is not printing up to all the numbers, but you can see it is significantly matching with whatever the numbers they have given here. So yes, our code is fine. Now let's check that if we increase the basis set size, what will happen? Let's delete the uploaded files from here. This is the beauty of coding, that you got the generalized code. Now just replace the file or integral and geometry, and you repeatedly can calculate all the things. So now this is in STS3G basis set. Now let's go to the d zeta basis set, and it's being uploaded. So that was 82.944, right? Now we are in the d zeta basis set, so which is like better than your STO3G basis set. Now check the numbers. First thing, that your atomic orbitals is doubled. Now it was 7, so now you are dealing with 14 by 14 matrix and 14 by 14 by 14 by 14 4-dimensional matrix, right? So your number of virtual is higher. Now you can see is that it took around 93 iterations to converge, and the value is minus 83.984, and previously it was 82.944. So when you increase the basis set size, your electronic energy is also reduced. So that is why, like, the higher the basis set, the better the number. So if you increase the basis set, your results got improved. And so it is 83.980. I think they have also given the numbers for the d zeta basis set. Let's check that whether we are getting the numbers correct. They have given all the integrals. I would encourage you to code it yourself and check all the numbers. Yes. So initially they got minus 132.79, and I got minus 127. I don't know why doesn't it match, but let's check the final number. They also took around 92 iteration. 83.9802460. So 83.9802460372372. So if you like round it, you can see the numbers is matching up to 10-12 decimal. This is fine. And the last check that we'll do now, the double zeta basis set with a polarization basis set. So it is even a higher basis set, right? So we'll check with this number. So this is their output, and we'll calculate it ourselves. So this is the files for the d zeta with polarization basis functions. Yes. So it was 83.980. Now let's check the number. It is 84.011. Right. It is even lower. That was first with the STO3G, it was 82.944, then 83 point something and 98, and now you can see it is 84.011. And now check out the number of atomic orbitals. Now the number of atomic orbitals, so initially it was 7. Now with the d zeta it gone to 14. Now it is 26. So now you can imagine that how many numbers of the matrix can be. So this number in the typical calculations actually goes to uh, 700, 800, 500 with large basis set, and so it is completing within 2 seconds, right? So in the so for the big molecule it will take days for to complete the SCF iteration itself. Okay, now let's check out the final number. It is 84.0111888, and they have given the value here, I think pretty large numbers because of the larger dimension of the basis set. Yes, 84.011188854711547. So it is matching exactly, right? So the code is fine. I will update this code in the slide, and I will encourage you to code it yourself once. And in the next class, so today I think I won't start this problem. It will take some time, and this is week 10, and I think in the coming class you will be taught about the annihilation and creation operator, and then I think it will be better to discuss this problem. But yeah, in the next class I can discuss this problem, and if you are interested, uh, or if I get some time, I will discuss the coding part of the additional concepts here. So again, let me show you one thing is that whatever the first problem I have shown you, this is basically the same thing. Density multiplied with the operator form, and you can calculate the average value. It is used everywhere in the quantum chemistry code and wherever. Then you can do a population analysis. We can try to do it, but yeah, I think it will be even better if you do it the molar pressure production theory second order. If I get some time and if you're interested, just let me know. And yeah, so we'll call it off now. Okay, thank you.